Okay, morning. The plan for today is to complete the lecture on sensitivity analysis, and then we are gonna discuss the second exam. If you haven't noticed yet, the exam grades are already posted, so you can look at your grade online. And performance was good. We will talk about the physics later, but I think in general, the majority of the students did over 80, which is good. We'll talk more about the exam later. So in our previous lecture, we started the discussion on sensitivity analysis from a graphical perspective, using a problem with two decision variables, so we can illustrate the changes in terms of how the feasibility and the feasible region will change as we make changes to some of the coefficients in the linear programming model. And we specifically look at two cases. The first case was for the right-hand side of the constraint. So we saw as we increase or decrease the values on the right-hand side of the constraint, how that changed the feasible region in the solution space, and also how that impacted the optimal solution. And the idea was to compute a rate of change, meaning that if you increase the size or the values on the right-hand side of the constraint, we can also obtain a measure of the rate of change and make decisions based on that. Meaning that, for example, as we define the dual price or the shadow price, that can tell us how much of an increase in the objective function you can obtain as you increase the right-hand side of the constraint by 1 unit. And then you can use that information to make decisions. And we also discussed the changes in the coefficients in the objective function. The idea was to see what were the feasibility bounds in terms of us being able to make changes to those coefficients, making sure that if we increase or decrease those coefficients as we make decisions, we also focus on making sure that the optimal solution will not change. So we defined the feasibility bounds, and we were able to tell, okay, I can increase let's say the profit of this product by this much and still keep the same optimal solution for my problem. And that will result on having this increase in profit. So today what we are going to do is we're going to perform the same type of analysis from an algebraic perspective, based on under the assumption that we are now going to handle problems that have more than two decision variables. So if we go problems with 3 or more decision variables, then doing the analysis graphically is very complicated. So we have to rely on the algebraic analysis to obtain the same insight from our solutions. And that's what we're going to do today. So the algebraic sensitivity analysis, this section demonstrates the general idea of sensitivity analysis using algebraic methods. In two cases, as we did for the graphical discussion, two cases will be considered. The first one is the sensitivity of the optimal solution to changes in the availability of resources, meaning the right-hand side of the constraint. And the second is the sensitivity of the optimal solution to changes in unit profit or unit cost, which are the coefficients of the objective function. And we're going to use this example. This is one example that we have considered before. I think I extended this example a little bit. So now we're going to have 3 types of toys: train, trucks, and cars. And the daily times for these three, for the three operations. Let me just move this. So three operations are used to assemble three types of toys, and the daily available times for the three operations are 430 minutes, 460 minutes, and 420 minutes. The revenues per unit of toy, train, trucks, and cars are $3, $2, and $5 respectively. The assembly times per train at the three operations are 1, 3, and 1 minutes. And the corresponding times per truck and per car are 2, 0, and 4, and 1, 2, and 0 minutes. A zero time means or indicates that the operation is not used for that particular type of toy. So now we're going to have three decision variables, which represent the daily number of units assembled of train, trucks, and cars, respectively. And the associated LP model is given as follows. So we're going to have X1 for train, X2 for truck, and X3 for car. And our objective function is to maximize that profit, which is $3 for trains, $2 for trucks, and $5 for cars. And we're going to have three constraints. Each constraint will be associated with an operation, which we have a specific capacity associated with it. And those capacities are in terms of minutes, which are listed here in the first bullet. So for operation one, we look at the requirements per product. So it's 1, 2, and 1. So the first constraint is X1 plus 2X2 plus X3 less than or equal to that capacity for operation one. And then for the second operation, we go back to the requirements 3, 0, and 2. So we have 3X1, no requirement for operation 2, and then 2 minutes for operation 3, less than or equal to 460. And this is for operation 2. And then for the last operation is 1 minute, 4 minutes, and 0. So X1 plus 4X2 plus 0 less than or equal to 420. This is for operation 3. And then the decision variables have to be greater or equal to 0. Okay, so this is the formulation, and this is the problem that we are going to use to explain the algebraic sensitivity analysis. And so we are trying to optimize making decisions in terms of how many of each products we are going to produce. And we have a capacity limitation for each one of the operations, and we are trying to maximize our profit. So this is the formulation one more time. And then after solving this problem, we use slack variables. I'm calling these slack variables X4, X5, and X6. So I'm adding those to each one of these constraints to make them equality. So after solving the problem using those slacks, so again, what I'm trying to say is these constraints are going to be X1 plus 2X2 plus X3. In this case, we're gonna have an X4 equal to 430, then 3X1 plus 2X3 plus x5 equals 460, and then x1 plus 4x2 plus x6 equals 420. So after setting up this constraint into the standard form, I can solve the problem, and this is the optimal solution after applying the simplex method. So this is the optimum solution, or this tableau is showing the optimal solution after applying the simplex method. So now, I mean, I'm not going to go through the, yes.
Regarding location, so it says 4, 5, 6 are our stack. Is different location?
Is yes. So it is just a decision variable, and we can name them x1 or x4 as long as you know they're representing the slack component. It's still the slack. Yeah. So these are slacks.
When I was studying before online, I found many
Mhm.
for both slack
X's. Yeah, so now we are transitioning. Like at the beginning, I was using that notation to make everything pretty clear. So an S basically is representing a slack, and E was representing an excess variable. But in general, those are decision variables, all of them. So it doesn't matter. So now we are basically assuming that you understand those concepts. So we are using the same notation for decision variables now. Okay, so I'm making those notes just to make sure that you are aware that those are the slacks. So this is what we are. So if you see the original object, the original constraints, now in red you have the equation form in which you have the slack variables. And then after applying the simplex method, this table at the bottom of the slide is showing the optimal solution. So if you can observe, this optimal solution is telling us that the profit is here and that you have produced x2 equals 100. So these are the trucks. So x2 equals 100. x3 equals, which are the cars, 230. And then x6 is a slack. So x1 equals 0. It's a non-basic variable. So you're not producing anything for the trains. And that's the optimal solution for the problem. Yes.
It looks like it's not feasible.
Why?
Because it's not.
The first constraint is 2x.
No,
Yes.
sorry.
Yes. Yes. So it's 430. Yes. So the idea now, if you observe this solution, what this is telling us is you still have some slack here that is unused, right? So this is basically associated with the operation number 3. So this is telling us we still have around 20 units of time or available of this resource that is not used. But the optimal solution, based on the resources that you have available, this is the optimal solution. So now we want to go into the sensitivity analysis using this information. So I already answered these questions. So how many trains? So again, the trains are x1. So trains are going to be 0. How many trucks? Trucks are x2. So 100. And then how many cars? Cars are x3. So this is 210. And this is coming off from the optimal solution of the tableau. Okay, so for the determination, again, we are looking now at the first case of the sensitivity analysis in which we're gonna study the changes in the right-hand side of the constraint. So we are gonna be focusing on this piece. Okay, so we are going to look at changes in the right-hand side of the constraint. So suppose in order for us to study changes in the right-hand side, we are going to use D1, D2, and D3 are the positive or negative changes made in the allotted daily manufacturing time of operations 1, 2, and 3. So we are now going to represent the changes that we are going to make to this right-hand side. Those could be positive or negative, meaning that you can increase or decrease 430. You can increase or decrease 460. You can decrease or decrease 420. We are interested in understanding how much you can increase or decrease this to keep the same optimal solution, and also to study what will be the impact of increasing or decreasing those capacities for those resources. So we are going to model those changes using D1, D2, and D3. And I'm putting those, we are adding those to the right-hand side of each one of those constraints. So that's what you're observing here. And those are used again to represent the changes made to the allotted daily manufacturing time for each one of the operations. So to express the optimal simplex tableau of the modified problem in terms of the changes D1, D2, and D3, we first rewrite the starting tableau using the new right-hand sides, 430 plus D1, 460 D2 plus D2, and 420 plus D3. So what that means in terms of our initial tableau is, if you look at this table, if you set up the initial tableau to solve this problem, this is going to be the initial tableau. Okay, so we have the coefficients for the objective function in row 0, and then we have the coefficients for each one of the constraints in rows 1, 2, and 3. And you see that the initial solution for this problem is given in terms of the slacks. Right, so these are the slacks, and that's why we have those as basic in the initial tableau. So for us to perform these sensitivity analysis in terms of the right-hand side of the constraint, we have to set up that initial tableau differently. Okay, so now this is the original tableau in yellow, and we are adding those 3 extra columns to this tableau for D1, D2, and D3. And you see those are listed after the right-hand side column. D1 is associated to the first constraint, so that's why that one is listed, or this one is listed in the first constraint. D2 is associated with the second constraint and 460, and D3 is associated with the third constraint. And what we are going to do now is we're going to solve the problem the same way we did before, with the only difference that any operation that we apply to this yellow table is also going to impact the first 3 columns. Okay, so these first 3 columns are not decision variables. Okay, I don't want you to get confused. D1, D2, and D3, they are not decision variables. They are there just to illustrate the changes in the right-hand side. And this will make more sense in a minute. Okay, so the only difference now, if you remember from this previous formulation, we are adding D1, D2, and D3 to the right-hand side of the constraints. So in the initial tableau, they are going to be represented by these 3 columns, D1, D2, and D3. If you notice, these 2 shaded areas are the same, are identical, right? 0, 0, 0. This first column for X4 and D1 is the same. Second column for X5 and D2 is the same. Third column for X6 and D3 are the same. Okay, so So the idea is that I can illustrate that, and you can see that what we are doing and how that connects with the initial tableau. Hence, if we repeat the same simplex iterations as in the original model, we solve this problem. This is the columns in the two highlighted area will also be identical in the optimal tableau because they have the same coefficients at the beginning. And if you perform the same operations into finding the optimal solution for this problem, since they have the same coefficients at the beginning, at the end, they should be the same. And that's what we are observing here. This is the optimal tableau. The right-hand side, this is telling us that this is the optimal solution. Okay, so Z is 1,350, X2 equals 100, X3 equals 230, and X6 equals 20. What I want you to see is that at the end, in the optimal solution, this area where the initial solution was given, right? The initial solution was given by the slacks. After performing all the iterations, those two shaded areas are the same, which means that if we can perform by using the original tableau without having to add these three columns, we can still get the information that we need to set up the dual values for each one of the constraints. So this is just illustrating that point. You can go both ways. You want to add those three columns, at the end you're going to have the same values for the coefficients. Okay, so we can use this information to actually make the analysis representing the changes in the right-hand side of the constraints. So this is, and this, they are the same. So the new optimal tableau provides the following optimal solution. So we have the shaded areas, and if we set up Z now, it's equal to this 1,350 plus D1 plus 2 times D2 plus 0 D3. And X2 is going to be equal to 100 plus 1/2 plus, D1 plus minus 1/4 D2. So that's X2. X3 is going to be equal to 230 plus 0 D1 plus 1/2 D2, and X6 is going to be equal to 20 plus minus 2, 20 plus minus 2 D1 plus 1 D2 plus 1 D3. Okay, so our solution now is stated in terms of the right-hand side and the coefficients for D1, D2, and D3. Okay, so this is our solution. Okay, so these are the columns representing my solution. So the optimal solution based on this information is giving us some information. For example, the dual prices or the shadow prices, the value of the objective function, can be written in this way. Z equals 1,350 plus 1D1 plus 2D2 plus 0D3. The equation shows that a unit change in operation 1 capacity changes the optimal solution or the objective function value by $1. A unit change in operation 2 would change the profit by $2, and a unit change for operation 3 would change the profit by $0. And that's all coming from that objective function value, which is 1,350 plus D1 plus 2D2. So for example, if you increase D1 by 1 unit, you know that you're going to increase the profit by $1. So let's say D1 equals 1. Then 1 times 1 is going to increase the Z value to 1,351. Same thing with D2. If you increase D2 by 1, let's say D2 equals 1, then you're going to multiply that times 2, and that will increase your profit by 1,352. If you increase D3, it's not going to make a difference because that's going to be multiplied by 0. So if you increase the capacity of operation 3, you are not generating any new profit. Okay, so this information is really important because it's telling you if you increase one of these operations, how much of an additional profit, or if you increase the capacity of one of these 3 operations, how much of an additional profit you can increase your solution with by an additional unit of each one of these operations. And as you can see, based on this information, it looks like operation 2 is the one that's giving you the higher increase in your profit by increasing the single units of operation. So this means that by definition, the corresponding dual prices are 1, 2, and $0 per minute for operations 1, 2, and 3, respectively. However, we also have to look at the feasibility range. So the current solution remains feasible if all the basic variables remain non-negative. That's it. We go back to these equations. I need to make sure that all of x2, x3, and x6 remain greater or equal to 0. To make sure that my problem is still feasible. So what I do is the following: x2 equals, so in order for them to remain feasible, I need to make sure that this expression is greater or equal to 0. x3 equals to 230 plus 1/2 d2 is greater or equal to 0. And x6 equals 20 minus 2d1 plus d2 plus d3 is greater or equal to 0. So simultaneous changes to d1, d2, and d3 that satisfy these inequalities will keep the solution feasible. So if I decide to increase d1 by 1 unit, I need to make sure that that change is not impacting these equations. For example, if I make d1, let's say 11, and d2 and d3 0, I know 2 times d1 will be 22, so 20 minus 22 will not be greater or equal to 0. So that will make your problem infeasible. So my changes for d1, I need to make sure that any change that I make to d1 or any increase that I make, if I make d1, let's say equal to 10, I know this condition will be satisfied. So that's feasible. But if I make d1 11, this decision variable will be negative. So my problem will become infeasible. So changes have to be constrained by these feasibility bounds. So the new optimal solution can be found by substituting out the values of D1, D2, and D3. Okay, so suppose that the manufacturing time available for operations 1, 2, and 3 are 480, 440, and 400 minutes. So now we're changing these values from the original coefficients. Let's go back to the original coefficients. The original values for these operations were 430, 460, and 420. Okay, so let me make a note here. So the original values, 430, 460, and 420. For operation 1, 2, and 3. Okay, so those are the right-hand side for the original problem. So now that I know that this solution has to be greater or equal to 0, and that simultaneous changes D1, D2, and D3 that satisfy these equalities will keep the solution feasible, I want to see if these changes that I'm proposing are from 430, I'm making D1 equals 480. From 460, I'm decreasing operation 2 to 440. And from 420, I'm decreasing the third operation to 400 minutes. So if I look at the values for D1, D2, and D3 for these three cases, this is going from 480 to 430. So I'm increasing this by 50 units. This is going from 440 to 460. So I'm decreasing this by 20 units. And this is going from 420 to 400. So I'm decreasing this by 20 units. Substituting in the feasibility conditions, we get the following. So now I'm going to substitute these changes. So this is D1, this one is D2, and this one is D3. So I'm going to substitute these values here. X2 equals 100 plus 1/2 times 50 minus 1/4 times minus 20, and this is equal to 130, which is greater than 0, so this is still feasible. Okay, so I can make that change for D1. At least it satisfied the condition for D1 or for the first operation. Let's check X3. 230 plus 1/2 times minus 20. This is equal to 220, which is greater than 0. Also feasible. And then I have X6, 20 minus 2 times 50 plus minus 20 plus minus 10 equals minus 110. So this is less than 0, so that this one becomes infeasible. Okay, so if I make these changes to the right-hand side, if I increase D1 by 50 units and decrease D2 by 20 and decrease D3 by 20, that's going to make my decisions variables, at least X6 is going to become negative, which is going to tell me that this solution is not feasible. Okay, so I cannot implement these changes that I'm recommending. I'm not going to be able to keep the same optimal solution if I proceed with those changes. So my solution is no longer optimal. So let's look at another set of changes. So now let's say that we make 1 400, 2 448, and third operation 430 minutes, the right-hand side. So D1 in this case will be minus 30, D2 is gonna be minus 12, and D3 is gonna be 10. So if I substitute this into my equations again, X2 is 100 plus 1/2 times minus 30 minus 1/4 times minus 12. And this is equal to 88, which is greater than 0. So this remains feasible. X3 equals 230 plus 1/2 times minus 12. And this is 224, which is greater than 0. So it's also feasible. And then X6 equals 20 minus 2 times minus 30 plus minus 12 plus 10 equals 78, which is also greater than 0. So this is also feasible. So these changes that I'm recommending in this example now, decreasing D1, D2 by minus 30 and minus 12 respectively, and increasing D3 by 10, are keeping my solution feasible. Yes.
But your Z value is less, and you're like increasing how much resources you don't use to increase the slack rate. Why would we do that?
So say that again.
So our Z value is less.
Yes, so that's true. Yes. So the C value in this example, originally the objective function values was 1,350. So the new optimal feasible solution is 1,296 units. So the change is based on the changes that we made into the capacity of the right-hand side constraints, right? And you see that now with those changes, you basically, if you look at the first resource, we are decreasing the capacity of the first resource by 30 units, decreasing the capacity of the second resource by 12 units, and then increasing the capacity of the third resource by 10 units. That optimal solution is changing also the numbers that we are producing per product, right? So now X1 equals 88, X3 equals 224, and X6, which is a slack variable, is increasing, which means that you have additional slack available now for the third operation. With those availability, that is the optimal solution. Okay, so if you compare the optimal solution with the original one, the changes that we made to the availability of the resources is impacting how many units you can produce, right? So let's go back to this one. Right, so in this, we have 100 and 230, right? Now we are basically decreasing also how many of those we can produce, right? So having less resources, so the optimal solution location is not changing. And if you remember our discussion from the graphical method, as you make changes to this right-hand side, you're moving these constraints to the left or to the right. So basically what's happening here is you are decreasing the size of your feasible region because now you have less resources. The optimal solution will be located at the same point, but the numbers in terms of the units that you can produce is less because now you have less flexibility in terms of how much space you have to produce units. So I don't know if I'm answering your question. So it's not a better solution. It's the optimal solution based on those resources, right? given those resources that you are, and remember, that's part of the analysis. So we want to see if increasing or decreasing these resources will provide us with some type of benefit. And as you can see here, that's not the case. You are not improving your profit. And then if you look at the slack, you're basically saying, okay, initially, I was just keeping my third operation. I only had 20 units of slack. Now with these changes, I have more units of slack, meaning that I have more of this resource that is not being used. So that would not be the, I mean, if I were a manager, I would not consider this solution because I had a better setup with the initial production or the initial setup for my capacity. But the idea of the exercise is that you can see, even though it's not better, still a feasible solution for the problem, given those limitations. So let's go to the next one. The given conditions can produce the individual feasibility ranges associated with changing the resources one at a time. So a change in operation one time only means that D2 and D3 will be equal to 0. Okay, so if we only look at operation one, we're going to set up D1 and D2 equal to 0. And then we are going to see what's going to be the feasibility range just for D1. So simultaneously, condition does reduce. If we make D2 and D3 equal to 0, X2 will be equal to 100 plus 1/2 D1. And these have to be greater or equal to 0, which means that D1 has to be greater or equal to minus 200. Remember, D1 is not a decision variable, okay? So D1 is just a change. And we are making sure that if we establish a feasibility range for each one of these representation of increases or decreases for the right-hand side of the constraints. So X3, which is 230, is always going to be greater than 0. And X6 will be 20 minus 2 times D1. In order to make this greater or equal to 0, D1 has to be less than or equal to 10. So this means that the dual price for operation one is valid in the feasibility range minus 200 and minus 10, or less than or equal to 10. So as long as D1 is greater than minus 200 and less than 10, the dual price for operation one will be valid. That dual price, if you remember, was defined here. So this dual price one, the unit change in operation one capacity changes by 1 unit of increasing D1. So that is going to be feasible as long as D1 is between these bounds. Okay, so you can increase it to 1, you can increase it to 2, to 3, to 4, to 5, up to 10. If you increase it to 11, it's not going to be valid anymore. It's going to make your problem infeasible.
So this is almost like a new optimization problem.
Yes, so basically what you're trying to, so the first thing you have to remember is the optimal solution location will not change, okay? So if you start with a problem, you solve that problem, and now you're making a sensitivity analysis based on the assumption that your analysis is going to be bound in a way that you're going to keep the same location of the optimal solution. So now the question is, you found those bounds, you're finding those bounds in which you can make changes and you keep the same location of the optimal solution. So that will allow you to make, not changes, but analysis in terms of how much of an increase you can create for some of these resources without changing the location of the optimal solution, and then study the impact of those changes. So we are setting up the bounds for each one of these dual variables or these dual coefficients. And if we continue in a similar way, the feasible ranges for operations 2 and 3 are minus 20 D2. So D2 has to be greater or equal to minus 20 and less than or equal to 400. And D3 has to be greater or equal to minus 20, and it could be as big as you want, because it's not going to make the problem feasible. So in summary, everything that we have done is to set up this table. So what this table is stating is for operation 1, operation 2, and operation 3, what are the dual prices? Okay, so this dual price is telling you if you increase operation 1 by 1 unit, then you're going to increase your profit by 1 unit. If you remember this example, we go back here, this example that you were asking for, what happened here is that you decrease your first operation from 430 to 400 units, right? So that's going to decrease your profit by 1 unit per minute, by $1 per minute. So you went from 430 to 400, that's its decrease right there of minus 30 units. Same thing for D2. You decrease that by minus 12, and you know that the dual price for the second operation was 2. So this is going to be 30 times 2 times minus 12. So it's 54, right? So if you decrease, if you subtract 54 from 1,350, this is the solution. That makes sense, right? The dual prices are associated with this change. So you decrease this T1 by minus 30. The dual price was $1, so that's a decrease of minus 30. For the second dual price, the decrease was minus 12. Dual price was 2. So 2 times minus 12 is 24. 24 plus 30 is 54. So 1,350 minus 54 is 1,296. And that happened because you decreased those 2 operations. If you increase the operations, then you should see an increase in your profit. And that is the type of information that we want to understand. So if you were to make decisions about what to do with your process, you know that this is the one that is going to give you the higher benefit, right? The dual price is telling you increase operation 2 by a unit, you get $2 additional per minute. But you have to make sure that you understand your feasibility range, because if you go outside that feasibility range, the problem will become infeasible. So what this is telling you is the minimum you can go is 440. Your current is 440. And the maximum you can go to increase this second operation is 860. If you go outside that bound, then you will make the problem infeasible. Okay. Questions?
So,
yes.
Looking at the, I don't know, you still call objective functions the various units?
Z is the objective function, yes.
So looking at the objective function, we see that the coefficient for T, yeah, it is the biggest. Right? So we can say that the most efficient will be just increase max D and everything.
In terms of increasing your profit, the right way to go is to look at operation 2. Yeah. Yeah. It will give you the highest increase by unit of time. Yes. So if you have to make decisions in that sense, you will have to go and try to increase that as much as possible, because that will give you the highest benefit. Yes.
These ranges are only applicable if you only increase that one thing.
That one, just that one.
If
Yeah.
you do a little bit of the top, a
Yeah.
little bit of the title.
Yeah.
So keep 0, just increase D.
Yes. Exactly. Exactly. So that's the information that we are getting from this. You can by solving the problem, running the sensitivity analysis, like, can I improve my profit oh yes, let's look at the dual price, the shadow price. Okay, this one is giving me the highest benefit. Remember, you have to keep in mind, as we discussed in the previous lecture, obviously increasing a unit of time of a resource will have a cost associated to it. So if the cost benefit also good, or if it's positive, because if it's gonna cost you more, let's say it costs you $3 to add a unit of time to this resource, and you're only getting 2, that might not be the best way to go. We are maximizing, yes. So that's the other piece, and we went through that discussion with the questions in the previous lecture. So now let's look at the second case. Yes, go ahead.
Could you open the question itself, the very first slide?
Yes. You want to see the first, this one?
Yeah.
You're maximizing the profit, and these are the constraints associated with the capacity of your process.
So basically, based on what I just said, that we can keep everything 0.
You want to, what we are discussing is the increase of this size. So how much you can increase that size and make an improvement in the profit. So if you increase this to 431, it's going to increase your profit by $1. If you increase this by 1, it's going to increase your profit by $2.
That's it. When I do all charts.
Well,
The maximum spend.
yes, exactly. So essentially what you're going to observe is you are, well, not necessarily, because it's going to be linked to the requirements. But what this is going to do is it's going to open the door to, let's say, producing, you're going to have to solve this, because you spend more time on X1, but that's not the one that's giving you the highest profit. What if you go back to this, you see X1 is equal to 0. So you're only producing X2 and X3, right? So your solution is basically telling you it's more profit for you if you increase, your solution is not going to change, remember. The solution will stay in the same point, but what's going to open is for you to produce more of these 2 products, X2 and X3. So if you see X3 is giving you the highest profit, so you don't need operation 3 for X3. You only need these 2 operations for this product that gives you the highest profit. And this one is just consuming 1 unit. This one is consuming 2. So by increasing this, you are able to produce more cars.
Yeah.
Yes, so that's going to increase your profit.
And to be allowed, it would be allowed to increase. And
when you can increase up to a certain point, and that's the feasibility range.
And 2 other constraints would just remain the same.
The constraints are, this side is not going to change. What's going to change is this side. Yeah. Good questions. So let's see if we can go through the second case, because we have to talk about the exam, so we still have time. The second case is changes in the objective function, or the coefficients of the objective function. So this is the concept of the reduced cost. So in the right-hand side discussion, we're talking about the dual price and the shadow price. Now in the objective function, we're going to talk about this concept of the reduced cost. In the TOEICO model, the objective C equation in the optimal tableau can be written as follows. Okay, so that will be the objective function value minus the coefficients for X1 minus the coefficient for X4 and minus the coefficient of x, which is what we have here. The optimal solution does not produce toy trains, right? We saw that x1 is equal to 0. The reason can be seen from this z equation, where a unit increase of x1, which is x1 is not showing up here, so it means that it's 0. So if you increase x1 here, what's going to happen? If you see this objective function in the first bullet, right? Right. So that's why you end up producing 0 cars. I'm sorry. X1 was the trains, right? Because when you look at the optimal solution in that tableau, it's telling you that if you decide to produce that product, that's going to decrease your profit, right? So it's not good. It's not a good decision for you. So this is, this information that is in the final tableau is also giving us some insight of what's going on in your decision process. Again, x1 equals 0. Why is that? Why are we not producing any products of that type? It's because when you look at the optimal solution of the problem in the optimal tableau, this is telling you if you produce those products, that's going to go against your profit. The reason why is this product might be consuming too many of certain capacities of your operations. So it's more expensive for you to produce when compared to the other two. And the cost of producing that product is not justified by the profit that you're making. So that's why you end up making making 0. So the reason can be seen from the Z equation, where a unit increase in x1 decreases Z by $4. We can think of the coefficient of in the Z equation as a unit cost because it causes a reduction in the revenue. Facilitate the explanation of the objective function sensitivity analysis, first we need to define what the reduced cost is. So the reduced cost per unit is the cost of consumed resources per unit minus the revenue per unit. And that's what I was trying to explain. It's costing you more to produce this product. And when you compare with the revenue that you're getting from it, it's not justified. So that's what we call the reduced cost. It's more expensive for you to produce than the benefit that you're getting from that product. To appreciate the significance of this definition, in the original Toyco model, the revenue per unit of toy trucks was $2, is less than for toy trains, which is $3. Yet the optimal solution recommends producing toy trucks, X2 equals 100 units, and no toy trains, X1 equals 0. The reason is that the cost of the resources used by one toy truck is smaller than its unit price. So again, looking at the benefit cost ratio, even though your profit is, or the cost or the profit that you're getting for that product is smaller, when you compare with the cost of producing that product, you look at the difference, is more profitable for the company to go with the other product. We can see that an unprofitable variable such as X1 can be made profitable in two ways. First one is by increasing the unit revenue. So we can go to the objective function and increase the revenue that we want to obtain, or by decreasing the unit cost of consuming resources. Or we can change the way we are producing this product to consume less time. In most situations, the price per unit is indicated by the market conditions and may be difficult to increase at will. So for example, if you see that your iPhones are not selling because are too expensive when compared to the competition, or you end up, the benefit that you're getting when compared to the cost of producing the iPhone is negative, and you try to increase the price, but if the competition has smaller prices, then you might not end up selling those because the competition has better prices. So this is what this statement is trying to say. So in practical situations, you not necessarily have the opportunity to make those changes because the market is the one that is going to be dictating the price of the units. So increasing the price of a product might be difficult. So the other option that you have is to try to improve the way you are producing the product to make it less costly for your operation and then get a benefit of the product. And we can discuss that topic longer, but that's outside this discussion. But what I was trying to say is sometimes companies will have some of the products that are not bringing any profit as part of their catalog because those attract customers and they can buy other products. So if you take that product out of the catalog, even though it's not giving you any profit, they will not buy the other products. So you will keep that product even though it's not giving you enough revenue because that product is pulling some customers to buy other products in your company. So those are the type of decisions that you'll face also in practice. So it's a cost benefit, not only in terms of the profit that you make selling that product, but also in terms of attracting customers to buy from your other products in the company. The development is based on the definition of reduced cost. So in the TOICO model, let D1, D2, and D3 represent the change in unit revenues for toy trucks, trains, and cars respectively. The objective function then becomes, the following. Let me write that down. Is the maximization of Z equals 3 plus D1, which represent the change in the profit, plus 2 plus D2, X2, plus 5 plus D3, X3. Okay, so we first consider the general situation in which all the objective coefficients are changed simultaneously. With simultaneous changes, the zero in the starting tableau appears like this. So now, instead of just using the 3 by itself, we are using the whole expression as the coefficient. Minus 3 minus D1, minus 2 minus D2, minus 5 minus D3, and this is the row 0 for the original tableau. When we generate the simplex tableau, the optimal iteration will appear as follows. So if you perform all the operations using those coefficients as part of the row 0, these are the expressions that you are going to obtain in the optimal tableau. So this is the coefficient for x1, this is the coefficient for x4, and this is the coefficient for x5, and this is the optimal solution. Okay, so we're doing all this to illustrate the process. Obviously, if you're going to notice in the assignments, I'm not going to ask you to go through this process manually. I'm going to basically spend more time trying to get whether or not you understand what these coefficients represent in terms of making decisions, because you can obtain those numbers, those reports automatically from the computer. But I need to illustrate this so you know where those coefficients are coming from. So the new optimal tableau is the same as the original optimal tableau, except for the reduced cost. This means that changes in the objective function coefficients can affect the optimality of the problem only. So remember, for a maximization problem, we want these coefficients to be positive at the end, right? So we state that we have obtained the optimal solution. So you really don't need to carry out the simplex row operations to compute the new reduced cost. An examination of the new 0 shows that the coefficients of R taken directly from the constraints coefficients of the optimal tableau. Convenient way for computing the new reduced cost is to add a new top row and a new leftmost column to the optimal tableau, as shown by the shaded areas in the following situation. So if you have the optimal solution of your problem without, you can obtain those coefficients these coefficients of row 0 without having to solve the problems with these at the beginning. So that's what we're going to illustrate now. So if you have the optimal tableau, you can obtain those coefficients by performing the following operation. You add this row at the top, you add this column at the left, and then for the leftmost column, the top element is 1, right here, in the 0, followed by change di for basic variable xi. Keep in mind that di equals 0 for slack variable xi. So to compute the new reduced cost for any variable, multiply the elements of its column by the corresponding element in the leftmost column, add them up, and subtract the top row. So you're going to multiply this column by this column, and then you're going to add this coefficient at the top. So for example, the reduced cost for x1, let's do that one, will be equal to this coefficient times this coefficient times this coefficient, this coefficient times this coefficient, this coefficient times this coefficient, plus this coefficient. This one?
Yeah.
Those are the reduced costs that we are represent the change in the unit revenue for trucks, trains, and cars, respectively. So we are basically modeling those as.
I know that. I know
Yes.
that. Because like the top one was 1. It wasn't 1. Why?
Oh, okay.
So that one was left out.
You're talking about this coefficient.
Yeah.
Yeah, so that's associated with the objective function, and that's going to be 1. This is for row 0.
Oh, and because the last one is a slack variable.
Yes, it doesn't have, yes,
Okay.
exactly. So D2 is associated with X2, D3 is associated with X3, as you can see here as well.
Okay.
Yes. So, so the reduced cost for D1 will be equal to 4 times 1 plus minus 1/4 times D2 plus 3/2 times D3 plus 2 times 0 minus this one. So this is going to be equal to 4 minus 1/4 D2 plus 3/2 D3 minus D1. So if you look at this right here, is the same expression that we have here. So we can obtain that expression without having to solve the problem with these initial coefficients. And that's what we just illustrated. So we wanted to obtain this coefficient for x1 in the final tableau. We use the original optimal tableau to obtain that expression, which is right here. So the current solution remains optimal so long as the new reduced costs remain non-negative for the maximization case, right? So we want to make this greater or equal to 0. We thus have the following simultaneous optimal conditions corresponding to non-basic variables x1, x4, and x5. So those are 4 minus 1/4 D2 plus 3/2 D3 minus D1, and these have to be greater or equal to 0. 1 plus 1/2 D2 to be greater or equal to 0, and 2 minus 1/4 D2 plus 1/2 D3 greater or equal to 0. Okay, So remember that the reduced cost for a basic variable is always 0, as the modified optimal tableau shows. So for example, now suppose that the objective function of TOICO is changed from this original objective function to this objective function. So decreasing the profit by 1 unit for X1, decreasing the profit by 1 unit for X2, and increasing the profit by 1 unit for X3. Then D1 is going to be the difference from the original. Sorry, this should be 3 minus 2. Yeah. Okay. So it's not right. Now suppose the objective function is changed from Z. So the first change is 3 minus 2. Second one is 2 minus 1. And the third one is 5 minus 6. Yeah, so this is incorrect. This should be. Oh yes, so D1 equals 2 minus 3. So we are changing from 3 to 2. We're changing, so D1 is going to be it's decreasing by 1, right? So it's 2 minus 3 is minus 1. Then the second one is 2 is also decreasing, so it's 1 minus 2, so it's minus 1. And then the other one is increasing, so it's 6 minus 5. So this one is correct. And then let's see if this makes sense. So the substitution in the given conditions yields 4. Yes. So these are the conditions that we need to meet, right? So let's look at the first one. The first one saying is 4 minus 1 over 4 times D2, which is minus 1, plus 3/2 D3. So this is positive 1. This should be 6 minus 5 equals 1. So this is 1 minus D1. D1 is minus 1, so minus D1. And this is equal to 6.75, which is greater than 0. Satisfied. And then we have 1 plus 1/2 times D2, which is minus 1. So this is 0.5, which is also greater than 0. Satisfied. And then we have 2 minus 1/4 times minus 1 plus 1/2 times 1. This is equal to 2.75, which is also greater than 0, also satisfied. So those changes that we are proposing are keeping the solution feasible, okay, based on these bounds. Doesn't mean that they're gonna give you a better profit. What this is saying is, if you make those changes to the coefficients, your optimal solution will not change the location where it is. So the solution will remain feasible. The result shows that the proposed changes will keep the current solution optimal with a new value of z equals 1,350 plus 100d2 plus 230d3, which is going to be equal to 1,480. So that will increase your profit. The preceding discussion has dealt with the maximization case. The only difference in the minimization case is that the reduced cost or the z coefficients must be less than or equal to 0 to maintain optimality. Okay, so we have to talk about the sensitivity analysis with the solver. I don't want to do that quickly, so let's do that on Monday at the beginning of the lecture. But in general, what you are going to do with Excel is, once you solve the problem, you can click on the sensitivity report, and it will generate something like this in your screen. And everything that we have discussed today, you will find here. Okay, so for example, for the reduced cost, they're listed here, and this is the analysis for the objective function. Okay, so at the top is for changes in the objective function. So reduced cost is -4, so that's why you have a value of 0. The objective coefficient, this is the original objective function coefficient. And then this is telling you the allowable increase for that coefficient is 4. The allowable decrease for that coefficient is a very large number. So you don't have a bound for that that decrease. So the same thing, right? So this is the objective function coefficient analysis. And then in this one, you have the right-hand side sensitivity analysis report. So as you can see here, you have the chattel price or the dual price. So this is telling you, if you increase the right-hand side by 1 unit, you get an additional profit of 1 unit. If you increase the right-hand side of the second constraint by 1 unit, you get an additional profit of 2 units. And you have also the bounds here. So the allowable increase and the allowable decrease. So everything that we have covered in terms of algebraic method, you can see here the results. So Excel provides you with this information. Okay, so let me stop the recording. So if for those of you who are online, if you have questions about your exam, you can meet me during my office hours. So I will discuss the exam with the students that are in class now.